We are developing a set of applications. It's a collaborative work between different partners. Within ICCS, we have two applications, and then we have Cobra with Thomas and Tetra with Sergi. I will be starting by presenting the first two applications, and then they will be going through the rest of the two. So first of all, let me just give you an overview of what we are aiming within our tool suite and what we are trying to deliver here. This is actually an effort that is targeting specific stakeholders, the network operators, DSOs and TSOs, as well as renewable sources plant operators. So the applications are trying to deliver some tools which are trying to effectively improve the everyday operations of the network operators so that they can more effectively and more economically manage their grids, their assets, their equipment, so that they can eventually try to overcome certain issues like when to proceed with reinforcements on the grid, when to proceed with maintenance on the equipment. And the way that we are delivering all those results is by effectively utilizing available data that we have access on. It's like, as I said, 4 applications. The first one is more relevant to grid planning. The second one is more related with the scheduling of the intraday and the day ahead by utilizing available flexibility. The third one is more related with performance monitoring, forecasting, predictive maintenance. And the final one, it's an asset management optimization toolsuite. So the main thing that all the applications have common is that they are not 4 standalone applications. There are 4 applications which are somehow interacting with a big data platform, which is the big data synergy platform that we are developing within the project. So the platform is facilitating us as developers to have access on large-scale data, utilize the data which we acquire through contracts which are somehow made through blockchain, and they are respecting all the privacy and all the restrictive issues that any stakeholder would have. And then through the platform, we have the possibility to run analytics, workflows, and utilize available functionalities which use machine learning or AI techniques to have the specific results that we're trying to showcase. So moving on with the innovations that we have within our 4 applications, main thing is that we are trying, as I said, to deliver high value information to them so that they can effectively manage all their assets and their networks, plan the upgrades where needed, optimize all the operational activities within their industry, such as green power exchanges, the operational scheduling. And all in all, we are trying to transition to a more automated way of operations, to a more predictive based rather than preventive based maintenance, as well as to more flexible predictive planning rather than the traditional conservative planning that have been used to withhold so far. So that's in a few words what the asset management toolkit is trying to succeed. And I will proceed by presenting the first 2 applications, and then I will also give a live demo of the app so that you can have a better view on what everything is about. So moving on with the first application, which is the asset management, the infrastructure sizing, the grid planning application in anticipation of growth, of load growth, of higher penetration of renewable and storage. This particular application is targeting both distribution and transmission system operators. So any interested stakeholder could utilize the application. And then the main focus of the app is to analyze in detail the state of the network. The way we do this analysis is by performing power flow calculations, and then we identify all the issues within the network where we get overloadings of the equipment, when we get over or under voltages, and that give us indications on where we have criticalities and how to proceed either with planning or with acquiring flexibility through a local flexibility market. The main objectives of the app is the network assessment, showcase some reliability metrics, how often we see faults, and how big is the criticality of the events. We do that through a stochastic analysis, and then we calculate some initial KPIs such as reinforcement needs, how many lines or substations we need to upgrade, how much flexibility we would be able to utilize instead of proceeding with reinforcements, and then propose the solutions. So the app is available through the URL, and there is also a mobile version of the app. So I'll just proceed with the dashboard of the application. So this is the URL that I showcased before, and that's the how the application, the look and feel of the app. And it's actually showing us that, for example, we can log in. I'm actually already logged in through the app. The authentication of the user is through Keycloak. So any user, any stakeholder who has acquired access through the Synergy platform, they also have access on specific applications which they deem that they are interested in utilizing. So they could log in on the app. Now I am the user that is utilizing the app. And on the right-hand side, we can see some of the organizations that we already have data from, and we already analyze and utilize their data sets. So it's a list of two stakeholders. Both of them are distribution network operators. And here we can see the different components of the app. The first one is the network performance assessment component, where we perform the power flow calculations for stochastic scenarios. And then for different scenarios, we get an overview of KPIs, how often we get violations, how big they are, and various status indicators through a heat map, for example. I will go through all of them one by one right now. And then we have the second component, the network asset sizing component, where we get eventually suggestions for decision making, when to proceed with reinforcements, and what would be the cost of them. So in the first tab, it's the network topology tab. Here, now I'm again logged out because I wasn't using it for long. So in the first component, the network topology, we get an overview of the network diagram that we utilize. Here, for example, we have the topology of one of the stakeholders, and then we get on the left-hand side information about the different elements that we have on the grid, how many buses, how many lines, how many loads, generators, static or not, switches, external grid, and transformers, and the same one, for example, for the different stakeholders that we utilize. So this is the base network topology that we utilize. On the topology, we have access on historical data from the stakeholders, historical demand, historical generation. We utilize those historical values to create statistical information, to create stochastic scenarios, and then we perform power flows on that specific topology. So moving on to, for example, what different generation and demand scenarios we can get. Here we have an overview of the variation of the profiles for a couple of representative days for different seasons, and for different type of days, for example, for a weekday or for a weekend, and for different type of data, demand or generation. And we also perform two different assessment scenarios for different increase. So we utilize those historical values, we create the statistical profiles, and then we move on to overview of different results, where we have results for the buses and the lines of the components, and we can see how a line gets violated, or how often a bus gets violated, and we get the per unit values. For example, for certain lines of the grid, if we have values above 100%, above the nominal capacity of the line, it means that we have an overvoltage. And through the box plot, we can see how big is the violation, how much above we are the 100% limit, and how big is the overloading. So that can give us an indication on which lines get overloaded and how far we are from the actual acceptable limit of loading of the line. Then we proceed with selected power flow results. We can get an overview of injected active power, injected reactive power per bus for the different type of days and the different type of season, and then select the results also for different snapshots. For example, different combinations of demand and generation for peak values or for minimum values, and how the results of the active and the reactive power get affected. So moving on with the different tab, we also can have a heat map. The heat map through the different colors can give us the level of criticality of the events. For example, the closer we are to the red color, closer to the limits of the line, closer to the limits of the acceptable voltage limits, 10% above or below the actual nominal limitations. That would give us also an indication that we get a violation. So for here, we have two specific lines through the heat map where we can see that we have some violations on those specific lines, and it's above quite a lot of the 100%. And those results are for the different scenarios that I explained before for the different snapshots. Moving on to the frequency of violations, this will give us an overview of how often we have violations throughout the year. On the buses and on the lines for the specific network, we don't really see violations with regards to voltage, but we see violations with regards to the lines. So these are the specific lines that get more frequently overloaded. And on the right-hand side, we can have an indication on how big is the size of the congestion. Is it something that we should consider? Is it something that we should take into account that would trigger reinforcement or not? For example, we have all the lines that frequently get violated, but this next diagram here, the histogram, would give us an indication of how big is the violation above the maximum limit. And for most of them, we can see, for example, for line 3, that maybe we get frequently violation, but the loading above the maximum limit is around 5% above the limit. So it depends on how each stakeholder would treat this information, and it depends on their own methodologies or on how they want to proceed. Do they really care about these violations, or do they want to proceed and let the operations happen as they are without proceeding with reinforcement? So moving on with the network asset sizing, we can have an indication for different set of horizons for day, week, month, or year, and for different type of seasons and for anticipated penetrations. What would be the planning decisions for the stakeholder? They would have two alternatives. The first one would be either proceed with flexibility-based planning, which means they don't proceed with the reinforcements, they don't upgrade the line or the substation if it's frequently overloaded, but instead of that, they would buy flexibility through the local flexibility market, and this would give us the requirements for flexibility. So if you if you decide to proceed with flexibility, how much upward or downward flexibility you would need to buy, how often you would need it, for how many number of hours, and what would be the cost of the operator. Whereas if they decide to proceed with expansion-based planning, how many lines do they need to upgrade? How many substations do they need to upgrade? And how much would be the cost of the operator for these reinforcements? So that's all in all. And then maybe I can proceed with the next app, and later on we can have any questions. What do you think, Salima?
Yeah, it has been 8 minutes.
Yeah, sure.
You have 2 minutes, more.
Sure. Yeah. So moving on with the next application, this is more relevant to the scheduling for the next 1 to 72 hours. And then again, the target users are DSOs and TSOs, and we would facilitate them coordinate the scheduling between themselves. How many requirements with regards to flexibility the DSO has and the DSO has, and how they could coordinate by acquiring, and what eventually would be the scheduling of this flexibility for the next few hours for both of them. So going straight to the app, again, here we have two components. In the first one, for today and for the next 1 to 72 hours ahead,
if we click submit, we could see what would be the scheduling, what would be the requirements. So for the different stakeholders and for different types of buses, we can have the amount of flexibility requirements, so that if the DSO and the TSO proceed with acquiring this flexibility, they would avoid any congestion. So the tool is providing a service, congestion management services. And then the flexibility capacity requirements are calculated. The DSO and the TSO could proceed by acquiring this flexibility. And here we also have the dashboard of how much flexibility we have available from different resources that we are coordinating as network operators. And on the next graph, how much is the deficit, so that if we had this available flexibility, we wouldn't have the forthcoming violations that we have identified. So the app is actually utilizing available forecasts for the next day, for the next 1 to 72 hours regarding demand, generation, and forecasting. We utilize those forecasts, and then we perform the power flow calculations. We identify violations, and we identify congestion management techniques so that we would avoid those violations forthcoming. So after performing the analysis that I just mentioned, we can have a list of flexibility products which the DSO and the TSO would need. So how much flexibility they would need for the next few hours, what would be the type of the flexibility, when the start of the delivery would start, and what would be the end of that flexibility. So they can have this information, both the TSO and the TSO, and they would proceed with whatever decisions they want to make. In the second tab, the common operational scheduling, it's actually a dashboard, an interface where both the TSO and the TSO could see results on. Grupo Cuerva is a DSO, so they wouldn't have an TSO. So this application is only utilized by the Greek demo partner we have in the project, the head node, which is the DSO, and the IPTO, which is the TSO. And then we can have a list of conflicts, which means that for the next few hours, we might have the case that both of them would need to utilize flexibility. So we need to set a priority. We need to set a strategy, which would give us results on who has access first. And for us, it's the DSO who has access first, and then whatever remains, whatever comes, and the DSO doesn't need it, the TSO could use it, so that we can have also all these messages. The DSO has needs, but the TSO doesn't have flexibility requirements, or maybe for the next few hours there are no needs for the both of them. So it's a matter of coordinating between the DSO and the TSO, and a matter of providing a prioritization scheme for both of them. And then finally, we can have the scheduling for both of them for the next 1 to 72 hours ahead of now. So what would happen for the TSO and what would happen for the TSO if we had this priority scheme or if we didn't really have it. So that's more or less the second app. It's more relevant to short-term planning, whereas the previous app that I showed is more relevant to medium-term planning. But both of them have similarities with regards to the fact that we perform the power flow calculations with whatever input data we have at the beginning. So that would be a live demo for both of them. I think we can proceed with the other partners.
I'm Tom Hall from Cobra. I'm going to talk about our application. So our application is to what's trying to advance the performance monitoring, forecasting, and predictive maintenance of large-scale RES plants. So as you can imagine, this application is basically for RES operators. So anyone that will perform the operation and maintenance, or the owners of the plant. And the idea is to optimize the performance of the plant overall. So the main focus of the task was to use machine learning techniques to help to manage these plants and to optimize specifically the predicted maintenance and proactively avoiding faults that can occur at the plant or any loss in energy or downtime, for example. So they're based on 3 objectives. We try to, first of all, to get a single platform where we have all the information about the plant in in one screen. So this contains all the key KPIs in one place, and it's easy to see visually the performance of the plant. The second objective was to help with fault detection and maintenance. And finally, we wanted to create a tool that could help to forecast the production for the future for scheduling needs or any operation and maintenance. Okay, so now, sorry, similar to what Angelina was saying, we have a login to get onto this this app, and now I'm going to show you the app itself. Okay, so if I can share my screen. Sec. Right, you should be looking at the app now. Is that correct? Can someone confirm?
Yes, Tom.
All right, thank you very much. Okay, so this is the first, well, the main screen of the app. There's three, I'm obviously logged into this as my own account. There are three different sections of the app. We have the operational dashboard, where we have all the information, the key KPIs of the RES plant in one area. We have a part on anomalies detection, state of health. So this has two different tools, which is the fault occurrence inspector and the predictive maintenance. And then finally, we have the forecast. So we have a long-term forecast and a short-term forecast. Okay, so let's have a closer look at the operational dashboard, the enhanced performance monitoring, as we call it. At the top, we can see the key KPIs from the plant. So we have the performance ratio, the efficiency of the plant overall, the expected radiation, or the measured radiation, the active power output, and other measurements. And therefore, the first graph we can see is comparing the radiation versus the active power, so we can see basically what we're expected to get from the plant and what we're actually producing. And then we can see the radiation versus the overall energy. Okay, so the idea of this is to have information about the plant's performance at a quick glance. We can see exactly how we think it's performing, or if it's not performing as we expected. So moving down, just to give you a heads up, you can see here that this data used is from 2021, because currently we're installing new sensors in a plant, so we expect to have up-to-date data as soon as possible. But currently, just for this application, we're using data from 2001. Okay, so moving down, not only can we see the overall performance of the plant, but we can look at individual inverter level. So here we have information about the performance ratio of the different inverters in this system. In the system, there's actually 12 inverters. And here, by choosing a specific inverter, let's go with 22, we can see how the individual, or breakdown of the individual inverters, are performing. So here we have the individual strings of this specific inverter. So it's got 18 strings, and we can see that there's variations between the average current that passes through the string, and also the minimum and maximum. So we can look out for anything which is, well, anything which is not expected, any faults, anything that's performing well. Then finally, we've got all the information, the total information about the inverter's behavior, and we have the information about the weather in the area. So we have 3 weather sensors in this plant specifically, showing showing the temperature and the expected radiation. Okay, so let's move on to the fault detection. So the idea of the fault protection app is, well, it consists of a new approach to fault diagnostic and predictive maintenance. So what we're doing is we're using all the information from the operational dashboard to predict or to diagnose when there has been a fault in an inverter. So we can choose a single inverter. At the moment, let's go with 22 again. And we can see that, hold on, 3. right? And we can see that the system predicts when there is an anomaly in the inverter. So this is using the information from the current input and the overall power output, and predicting that a fault has occurred. And also using the table below, we can look at every 10 minutes, we can look at what the percentage probability that the fault has occurred. So we can see that these are quite accurate predictions in terms of detecting the fault, diagnosing the fault. The other part of the fault detection is for predictive maintenance. So this is an active fault detection system, which is comparing the radiation at the plant directly against the performance and giving the overall efficiency of the plant. So here we can see that if in the case where the efficiency drops over below 0.4%, then we believe that there's a fault. So therefore, an alarm will go off, telling the user that there is some kind of problem with the plant. Obviously, at the start and the end, this is negated when there is no radiation being produced. Finally, for the fault detection system, we have a prediction of the efficiency of the plant for the future. So a forecast about how the operation, the forecast about the probability of faults for the future. And the idea of this is to help predict when to perform predictive maintenance, or to have a good idea about the amount of production we will have in the following day. And again, we have a table breaking down the specifics. So finally, the last tab we have is the short and long-term forecasting. So let's have a look at the long-term forecast to start with. So this tool aims to, well, it uses information about previous and future weather conditions or weather predictions and previous production information to predict what will the production be in the future. Obviously, this is ideal for knowing what energy is going to be produced so we can sell it for the future, or for any operation and maintenance task. If we have a look at the short-term forecast, so the idea is to have, in the long-term forecast, we have, like, let me go back. In the long-term forecast, we have a week ahead or 10 days information about what we expect the production to be. And in the short term, we have 6 hours, 24 hours, or 48 hours. And we can, we are here using the forecast and putting the production on top so we can compare the production against the forecast. Now, in this case, we can see a strong deviation, and that's probably, well, it is due to the fact that, as I've previously said, we're using data from 2001. But in recent tests, we've seen that this forecast can be very accurate, and it can be very useful for RES plant operators. So that is all from our app. And now I believe I'm going to pass the floor to Sergi.
Hi, everyone. Here's Sergi from Metra. Now I'm going to give you a brief overview about asset management optimization application. And after that, I'm going to proceed with a live demo as my other colleagues. This application has as a target users DCOs and TCOs, and also the field worker team, because as I will show you, we have also implemented a mobile AR application. As a main focus of this toolsheet, we are trying to provide different models that optimize the maintenance management by enriching the available data with the results of a number of analytics and forecasts, and allow easy data storing from the field workers' perspective. The principal objectives are related to obtain the overall health score of each asset instance under maintenance. This will be calculated with different deep learning techniques using the SCADA data and also the even falls of each assets of these DCOs and TCOs. We will also provide an indicator to properly prioritize the scheduled maintenance operations. As I said, we will also forecast the future failures. And we will try also to early detection and logging different problems and faults. And regarding the mobile AR app, we are trying to provide different augmented reality visualizations of the measurements and indices of these different assets in terms of when the worker is in the field. This application has also this URL that is available right now. As the other applications, we are using logging through the Kik log. We can also use our Synergy credentials. As I said before, we have also a mobile AR app. So Angelina, please, if you can stop sharing, I'm going to show my screen. Okay. Here I'm using my Synergy credentials. I have my user connected with the Kirk company. So sorry, this one. So now we are showing the Kirk company information. Here, as in the main view, we can see all the registered assets. In this case, Kirk has registered 3 transformers. We can also see the current health status of each asset and also the last updated time of this health status. We can also see, just a second. Okay, in the map, it's supposed to be displaying the topology. I don't know what's happening. Okay, we click to a specific asset. We are moving to the asset details. Here, we can also see the current measurements of each asset. The last measurement, okay, it's supposed to be working in live, but sometimes we are not receiving live updates, so we are just displaying the last measurement that we have stored in Synergy. We can also see the current health score status. Right now, we can see that the transformer 2 is in a status healthy. In terms of our deep learning model, we are trying to give 4 different time windows where we can say that the asset is in failure, will fail in next 30 days, will fail in next 60 days, or is healthy. In this case, we have 4 classes where all of them has to sum 100%. In this case, the probability is distributed as we can see here. 99% is healthy, and only 1% is saying that will fail in next 60 days. So we can assume that this transformer is in healthy status. Okay. By another hand, we can also see the historical SCADA measurements. In this case, we are working with voltage and current. And for example, if we move to our historical data, we can see the voltage in a time period, also the current. Perfect. And here we have 3 other buttons where we can see the commit manual pictures. These ones, this application is implementing an API that is connected with the mobile AR app. So it lets the file worker post different pictures, as we can see here. We have one, and also different manual measurements that the field worker has taken in the field, just to post them. And when the field worker arrives to the office, just go to this user interface, check if all the measurements and also the pictures are correct. And if yes, they can commit the picture and also the measurements. These measurements are sent to the Synergy platform, and we can see the committed pictures here. And also we have here another graph just to see the manual metrics as historical as we seen here in the metrics SCADA data. Moving to the last section, it's pretty much the same as the main view, but here we are trying to sort the different assets in terms of priority of maintenance. Okay, we can also click on the asset. We will see the current measurement, and we can go again to the asset details through this other section. Right now, I'm going to show you a brief video of the AR application, okay, just to let you have an idea how it works. Okay, this video also let the user scan the QR code of a transformer. It is moved to the asset details. Here, the user can take pictures. These pictures can be posted to the user interface as shown before. And that's pretty much how it works. It can see also the available assets, and the mobile AR app can also post information. This is more or less my presentation.